Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, I'm Dr. James Wotton, the Chief Scientific Officer of Moss Quantum, and I'm going to tell you about quantum solutions for the creative industries. So, I thought I'd start by giving you a brief background of who I am. I'm one of the people who came to quantum computing by the normal route. I did a degree in physics, then a PhD in the quantum computing group at the University of Leeds. And then I came to Basel in Switzerland to be a postdoc and do more quantum computing research. And my research was at that time focused on quantum error correction. And at that time, we would do these simulations for quantum error correction processes with hundreds of qubits, when in the lab, you might get 2 or 3 qubits, and that would be the cutting edge. And it felt to me that what I was doing in my research was so far from reality that I wanted to do something that could actually bring quantum computing to the taxpayers who were paying for my research. So I made a citizen science game that was based on my quantum error correction research. And it was called Decodoku. I think it's still available on the internet in some places if you want to go and find it. And it allowed people to start thinking about how to do decoding um, in quantum error correction, but in the form of a game. This was in 2016, which was the same year that IBM put a quantum computer on the cloud. So one of the most advanced quantum computers at the time, which was only 5 qubits, but it was on the cloud. Anyone could use it. So what can we use it for? Well, given that in that year I was thinking about outreach and I was thinking about games, I thought about, well, what kind of game can I make run on a quantum computer? So I made a rock, paper, scissors variant that ran on a quantum computer, just for fun. That was before Qiskit even existed. This is how long ago this was. ETH had a similar SDK which could be used to access IBM's cloud quantum computer, and I made it using that. Now this led to me working more with IBM. I made a educational game called Hello Quantum with them while I was at the University of Basel. That led to me being an employee at IBM Quantum from 2018 to 2024, doing research, including research in quantum error correction, but also doing outreach and education, and continuing this idea of looking at the intersection of quantum computing and games. But while I was at IBM, what I became interested in was what games could benefit from within quantum computing. Um, and that's what I do even more of now at Moth Quantum, leading research on what quantum computing can do for games, art, and music, and all other creative endeavors. So that leads into who we are as a company. So there are many startups in the world now looking at applications of quantum computing for various industries, important ones like healthcare, boring ones like finance, but we're the only one to do the creative industry. So things like games, music, and visual art. So in our company, we do research, and we have a research team that is split across Switzerland and the UK, mostly based in Switzerland though. We also build products, so we have an engineering team that's mostly based in the UK, and we collaborate with creative people. So we're based currently, at the time of recording, at Somerset House, which looks very fancy from the outside, as you can see in this image. The inside is why I said at time of recording, because there might be a change in office in London. But in Basel, we're very happy where we are. It's at this Uptown Basel Innovations campus just outside Basel. So let's get into the actual presentation. We are using quantum computers for creativity at Moss Quantum, and this is just a natural continuation of the fact that since computers have existed, we have used them for creative endeavors. And if we look specifically at games, I like to look at these three milestones, where in the 1950s, people were putting games on computers, but they were usually existing games, and usually very simple games like tic-tac-toe or noughts and crosses. So this was usually at trade shows, as you can see a picture of here on the left, where someone would want to sell their vacuum tubes by um, putting up a booth at a trade show and showing that their vacuum tubes could play tic-tac-toe and hoping people were amazed by it and bought their vacuum tubes. It was an era in which you weren't really getting any novel gameplay experiences from running a game on a computer. So it wasn't really an era in which the computer was doing anything for games. It was an era instead where games were doing something for computers, i.e., helping people understand the technology, showcasing the technology, and trying to get people to buy the technology. Then we move on to the 1960s, where computational technology became more sophisticated and allowed novel gameplay experiences. It allowed things like Space War, which is the game that you see depicted in the middle here, where you fly around spaceships and shoot them. Two players fly around spaceships, shoot at each other, try and destroy the other player, all while in the gravity well of a star. It's pretty awesome. And it's not something you could do without a computer. I mean, even if you were to make your own spaceship and fly it around the gravity well of the star and shoot at your friend, you would probably still need a computer to get into orbit. So uh, this is a gameplay experience you need a computer for. It was also made to be fun, not just made to sell things. However, one caveat in this era, in the 1960s, was that the computational hardware that would be used to run these games was very expensive and limited to only the few who could get access to it. It would usually be these systems existed, for example, in research institutions like universities and were primarily used for research. It's just in their off time that you could play a game on them. It was only in the 1970s and beyond that games could justify the cost of the device on which they ran, and so you could get commercial successes like Pong. So this is, in some sense, the history of computer games. So now let's look at the history of quantum computer games. So we have already been through the 1950s of quantum computer games, where people have been looking at what games can do for quantum computers in terms of education, outreach, showcasing the technology, helping people understand the technology, helping people get hands-on with the technology. And this can be in games that don't use quantum computers at all, but are just about quantum computers or about quantum more generally. So things like tic-tac-toe, which you see here, is a tic-tac-toe version which uses principles of superposition. My game Decodoku that I mentioned earlier doesn't have any principles of superposition or entanglement, but is based on the principles of decoding quantum error correction. You also have Quantum Odyssey here, which is something which can teach you how to create quantum circuits. But also Q Cards is a card game where in the end, to see who wins, you have to run the circuit and you can run it on a real quantum computer. You have my old rock, paper, scissors and other games that run on real quantum computers. So you have this mix of them being about quantum computation or even running on a quantum computer, but always it's in this 1950 style education, outreach, showcasing. It's what games can do for quantum rather than what quantum can do for games. And we've got a couple of papers that I show on the slide here that you can go to check out more information on this. What I think we should be trying to transition into now, and what we're trying to do at Moth Quantum, is look at what quantum can do for games. And I think that one of the first things that people think about here often is, can quantum computers be used for better rendering of graphics in a game? And so I just want to start off by saying basically no. Now, can quantum computers be useful for rendering? There are some people that have argued that they can, but this would possibly be in cases where you can take a decent amount of time to sit there and render, like in a movie where you can spend a while rendering it because the rendering problems that you're solving are going to be shipped out to the entire audience. In a game, you have personalized rendering that needs to be done in real time. So the idea of using a quantum computer for that, to me, seems unlikely in any sort of near term. Um, this is because we really shouldn't be thinking, when we're thinking about what quantum can do for games, about trying to use the quantum computer every frame of the game, because that's not the kind of thing that a quantum computer is good at. Quantum computers aren't there to turn tasks that would take 1 second into tasks that would take 1 millisecond. People think of quantum computers as making things faster. That's true. But if a normal computer is already good at a task, a quantum computer is probably not going to speed it up very much, if at all. What a quantum computer instead will do is take a task that takes an unfeasibly long time, the kind of thing that you wouldn't even bother doing with a normal computer because it takes too long, and then does it in a reasonable amount of time. So the kind of thing that we can think of using quantum for in games is something like procedural generation. This is the algorithmic generation of content, because within this whole world of algorithms in procedural generation, there are many complicated tasks that can be solved. And because some of them would take so long to solve, there are many workarounds that people currently use to get around them. And then there are many issues in how well you can create the content given the constraints that you have to do these workarounds. So if you could drive straight at the computationally hard problems, then you could have more tools that allows you to do more complex procedural generation. And this means solving things like optimization problems and constraint satisfiability problems. I said earlier that there are many quantum software startups in many different areas. That's true. But often they all boil down to saying we're going to solve optimization problems and constraint satisfiability problems. So in some ways, we're just the same as other quantum startups in that regard. But every industry has its own unique um, conditions on what it means to solve them in the right way, in the right amount of time, in order to be useful. And we are the ones who are specifically looking to solve this for the creative industries. So procedural generation is also something that can take a little bit of time. You can think of it running in the timescale of a loading screen, or you can be generating one level of a game in the time that a player is playing the previous level of the game. You can also have massively multiplayer games so that the computational tasks that you are doing, the use of a quantum computer that you are making, is not just for a single player, but for multiple players at a time. So this, I think, is the area in which it is really most realistic and very realistic to use quantum computers for games. So I would say that procedural generation is actually the perfect field in which to look at the emergence of quantum computing, or indeed creative endeavors as a whole. Because in many applications, there is a right answer, and you have to get the right answer to be useful. And if you want to claim a quantum advantage, you have to get the right answer more quickly with a quantum computer than you could with a classical computer. And that can be very hard if you're calculating the ground state of a molecule. We have algorithms for quantum chemistry on classical computers that are extremely good and get the right answer to a very good degree of accuracy. If you're looking at factoring, you have to go to very high numbers in order to factor numbers that are cryptographically relevant. That requires many qubits, many gates, and will arguably push you to the era of fault tolerance, and so to quite high overheads in what you need for a quantum computer. But in creative endeavors, it can mean something different to be useful. Now, this is not when I'm talking about the future of procedural generation with quantum computers, where we are solving hard optimization problems and constraint satisfiability problems. There we do have right answers we need to get, and we need to get them faster than the classical computer in order to be useful. But before that, we can go through eras where doing something useful for creative people is more about just bringing something new, something that gives them a new perspective, something that is novel and interesting to them. And so we can already start to offer that now. Before we have a quantum advantage, we can offer it in an incredibly sophisticated way in the future when we have a quantum advantage, and between the two, we can just continuously get ever more useful and sophisticated. So more specifically, I think of quantum computing going through these three eras. One is where you think about your quantum software in terms of having less than 20 qubits, say. At this point, it's extremely easy to emulate it. You can emulate it on your laptop. You can emulate it on your phone. You can maybe emulate it on a little microcontroller if you wanted to. On the other extreme, we have systems with thousands of qubits, enough that they can implement fault tolerance, which will effectively get rid of noise and be able to implement the algorithms out of textbooks, such as Shor's algorithm, for example. In between the two, we have systems of hundreds of qubits, arguably beyond the ability to emulate what's going on there, so they can, in that sense, do things that classical computers cannot. However, they are not well behaved enough to do what you tell them to do. It is quite challenging to convince them to give you a good answer for whatever problem it is you want to run, and you have to put quite a lot of effort into trying to run a problem that will actually run well on these devices. So it's a very interesting era at the moment as we have devices with hundreds of qubits to try and figure out what to do with them. But in the creative industries, or creative endeavors as a whole, what we have found is that even in the era of emulation, there have been examples where what you could argue is quantum software, even though it's being actually run uh, on an emulator, quantum software being useful for creative people. So one example of this, as I'll talk about in more detail in a few slides, is something that I made called Quantum Blur, which actually runs more easily in simulation than it runs on real quantum hardware. But nevertheless, it has been useful to artists such as Libby Heaney, but also more extensively an artist called Roman Lipsky, who have been using it to create visual art. It's been useful for a game studio called MyTale, who are using it in their upcoming game called Clay. And other methods have also been used in music, most predominantly by the quantum music pioneer Eduardo Miranda, who is also associated with Moth, by the way. So the fact that even these very simple versions of quantum software bring something new and interesting and useful to creative people means that we know that as we move into the era of having hundreds of qubits, we can find things that are even more sophisticated and useful to creative people, and then get ever more useful until an actual quantum advantage arises. So I want to dwell a little bit more on quantum blur, even though this is something that I did not at Moth, but in my time at IBM. So this is Moth prehistory, but I think it's also quite relevant for what we're talking about here. So quantum blur is essentially an image manipulation effect. It's a way to take images, encode them as quantum states so that then you can manipulate them in that way. It's designed primarily to be used on simulators, or emulators as I like to say, and it was made very much in this 1950s era of education and outreach. It was intended to be the basis of hackathon projects. It was intended to be educational, to be someone's first way of playing with quantum computing, and it was also intended to be the basis of a paper and I wrote a paper, and you can see it on the slide here. However, it has been used for much more. So just to give you a bit of an overview of what quantum blur is, so if you have a monochrome image, it has a bunch of pixels. Those pixels have locations and they have brightnesses. So instead of the location as a coordinate x and y, we are going to assign it a bit string as an address. So one of these pixels is going to be 0, 0, 0, 0, 0, one's going to be 0, 0, 0, 0, 1, and so on and so forth. And then we use the amplitude of the bit string in a superposition to correspond to the brightness of the pixel. So there's this one-to-one correspondence between a superposition state and the image. But the only real detail of this, which is important and unique to the way we do it in quantum blur, is that we use so-called gray codes as our way of assigning coordinates to bit strings. And this is done such that similar coordinates are going to have similar bit strings. So that 2 points, if they are neighboring in the image, they will have bit strings that differ only by 1 bit. And this has the effect that, well, actually we'll see it more in the next slide. So what if we manipulate the image? Well, how can we manipulate the image? One way is quite simply, let's go on every qubit and do a tiny little small angle rotation. Then we are going to do something that doesn't change the image much, but it changes it a little bit. It's going to cause amplitude to exchange between certain bit strings, and therefore brightness to be exchanged between certain sets of pixels. And the way that we have chosen the bit string to coordinate mapping, such that nearby bit strings correspond to nearby pixels, means you get a bit of bleed of brightness into neighboring pixels. But also, if you have many qubits, more than 4 qubits, there are more than 4 neighbors for the bit strings, whereas there are only 4 neighboring pixels on the image. So you're also going to get non-local effects, you're going to get interference effects. It's going to be a weird effect, as you see in these 6 images at the bottom, where we start off with just 2 bright points, which actually corresponds to a GHZ state, by the way. And then as you apply more and more RX rotations, the brightness bleeds out. And in the end, when you get to an angle of pi over 2, becomes this chessboard pattern. So we get interesting interference effects. Do those interference effects make a nice image manipulation effect? Well, that depends on your taste, but some people say yes. One other thing to note is that we find that it is actually useful to have entanglement in this, i.e. that the entanglement that is used in the image actually has a useful effect. It's not that it just happens to be there, but it is part of what's going on in this whole process. And one way we can see that is by using a simulator that allows us to turn down the entanglement and see how that affects the image. And you can see as you turn down the entanglement in these 2 images, well, actually this is the bond dimension used within the simulator. If you turn up the bond dimension, therefore turn up the amount of entanglement that can be captured, you get a good representation of the image. As you turn it down, you see that the image can't be captured so accurately. Okay, so the original application of this was intended to be terrain generation. So one of the first things that people used in normal procedural generation, non-quantum procedural generation, was just blur effects. You take some random points, you blur them, and it gives you a nice continuous landscape that you can use in a game, or a texture that you can use to make your CGI look slightly more realistic. And I thought, well, let's just use these interference effects as texture generation and use that to create landscapes within games. And so that's what I did. Here's an island that I made in a game engine that is rather Minecraft-like, as you can see, and it makes a nice little island, and you can go and explore it. It's pretty cool. This island is actually present in the corner of the game Kizkit Blocks, which was put out by one of my colleagues at IBM a few years ago. If it's still working, go and check it out. You might be able to find my island. It's also been used beyond my hackathon and game-based intentions as a serious tool for artistic expression. So there's a Berlin-based artist called Roman Lipsky who's been using it as one of his main tools for artistic expression for the last 5 years. Here's some images from an art exhibition that he put on a few years ago, and if you look closely you can see that among his beautiful art you will also find an interloper, which is a poster that I put up to explain the science behind it. And if you look closely at the poster, you might find it looks a bit familiar. In fact, these last few slides have been excerpts from that poster. So you can imagine yourself being at the gallery, being told about this work, although unfortunately you probably don't currently have a glass of champagne in your hand. So yes, he is still using quantum blur even now. These are some excerpts from his most recent work. I can even show you a little bit of this video of his most recent work. So here he's taken a LiDAR scan of his head and he's applying quantum blur. So he's applying these interference effects to the head. There's also the landscape in the background is being generated by quantum blur. And of course, this is something that is being rendered in 3 dimensions in a game engine. There's also a lot of more stuff going on here. It's not just a tech demo of quantum blur, it's a piece of art. So go and check out his website if you want to know more about what this series of works, which is called Quantum Babylon, is all about. However, let's move beyond quantum blur, because as I say, this is moth prehistory. It shows that even in this era of emulation, you can create tools that people in creative industries find useful. And so we already have established usefulness. This shows that we can already start to build products based around quantum software. So let's move out of quantum software that is designed to run on simulators and move on to quantum software that can also run on quantum computing or on actual quantum hardware. So the next step, the one that we're looking at the moment, is quantum reservoir computing. And we have an example of quantum reservoir computing that we're exploring at the moment, which is our first step out of the world of emulation and into the world of running on real quantum hardware. Because this current implementation that we're doing is equally at home on a simulator as it is on real quantum hardware. So it's based on this idea of quantum reservoir computing. Quantum reservoir computing is based on the idea of reservoir computing more generally, and reservoir computing is where you take a system with complex dynamics and trick it into doing a computation for you in a way that is quite mysterious. So what is a computer? It's something where you give an input, it does some stuff in the middle, and then it gives you an output. And so you give it an input, which is the input for your problem, you get an output, which is the output of your problem, and you're happy because it did your computation for you. In systems with complex dynamics, similarly, we can have a stimulus. We can have some way in which we introduce an input. And also we can look at what happens after that. We can take some output from that system of complex dynamics. So in some ways, that is also a computer, except what do you mean by input and output in this case? Well, you have to find some way, if you've got an actual problem you want to solve, of turning the inputs from your problem into ways that you can stimulate this complex dynamics. And where you are taking measurements of these complex dynamics to see how the stimulus affects it, you have to find some way of turning these outputs into the outputs you actually want from your computation. So in reservoir computing, what you do is you take a simple linear transformation to turn the actual measurement results of the complex dynamics into the output of your computation, and then you train that linear layer in order to actually produce the outputs of the computation that you want. So end to end, you have a way of introducing the inputs of a computation. In the end, you have a way of getting the outputs of your computation. In the middle, what is doing that computation, where there is a linear layer which you have trained based on what the computation is you actually intend to do, and there are some complex dynamics doing non-linear things. So if you've got a computation that requires non-linear processing, you know that basically it's the complex dynamics that are doing that processing, because the actual trained output layer is not linear and therefore is not complex enough to do the computation. But it's actually only the linear output layer that even knows what the computation is. The complex dynamics is something like a bucket of water where the stimulus is you poking it and the measurement outcome is you looking at the ripples. So, okay, that was a bit of a data dump. But this is just to say that you are taking complex dynamics, using them to be the powerhouse behind the computation, even though essentially they don't know what that computation is. But the more interesting the complex dynamics you use, the more easily you can trick them into doing a computation for you. So there are examples of this being done with water waves on a bucket of water. So you can check out more details about that in the paper that is referenced here. With quantum reservoir computing, you just use complex quantum dynamics in order to make the computation happen. And the fact that you only need to train a linear output layer means that if you think of this as a form of AI, often in AI you have to put in a lot of training data in order to train it to do the computation you want. But because there is so little that you need to train, you need little training data, and therefore, well, that's good. And just to emphasize why that's good, let's actually go to a specific example. So what we're using it for is, or what it was, the system that we have created was initially intended for, was to analyze a piece of music and then produce riffs on that music. Because QRC is great at time series data, where you have a list of data, and then you are going to, one after another, stimulate your reservoir to introduce those pieces of data, and then one after another you're going to keep measuring the effects of adding those pieces of data to your reservoir. And so you introduce this time series data and you get a time series analysis out. In our case, we are going to be training it to understand a piece of music, and then the time series analysis we're doing is to keep generating a new variant of that piece of music. And the fact that we only need to train it on a small amount of data means that you can just take a single tune and train it on that and produce riffs on that one piece of music. It doesn't need to rip off all of the music in the world to produce riffs on music. It just needs the one piece of music that you want to riff on. So this means that it becomes a tool that musicians can use if they've got a little piece of music and they want to get some inspiration about how they can extend this into a larger composition. They can use this quantum reservoir computing system as part of that creative process. So it's a form of generative AI in some ways, but it's an artist in the middle form, where the artist takes their own work and uses it as a tool to creatively expand on that work, rather than the way of stealing from artists and trying to replace them, as some other AI systems may be trying to do. So we're currently collaborating with a musician based in the UK who has been using this tool to create a new single, which will be out soon. And so this was given to them in a form that uses a simulator, and then they were able to go into their own studio, create some music. But then they collaborated with us to do a further analysis, which actually used real quantum hardware using a device called Garnet from IQM. This produced remixes, which were then incorporated into the original track because it provided new inspiration. So it just goes to show that this is us stepping out of the era of emulation into the era of properly using real quantum hardware. And it also goes to prove that this is an artist in the middle based technique, where they have really used this tool to create something that they wanted to create, and it's not just, one of these artists replacing generative AI things that we're not really big fans of anymore. Another application we used for quantum reservoir computing was in computer games. So if you take, for example, levels of Super Mario Brothers, you can also think of those as time series data. So there's different unique columns, and so you can think of a level of Super Mario Brothers as you have, three things that are just floor, and uh, then you have a question mark block, and then you have three more floors, and then you have this block, and then you have the mushroom block, and then so on and so forth. So if you label this kind of column 0 and this kind of column 1 and this kind of column 2, then your level just becomes a series of numbers: 0, 0, 0, 1, 0, 0, 0, 2, 3, 4, 5, 2, 0, 0, 0, and so on and so forth. So we break down um, the level into a piece of time series data. We can then just feed this into the exact same system that we use for music. It's going to learn the level and produce riffs on that level. And we can do that in the same time it takes to play a set of levels. We can generate a new set of levels, meaning that we can create a game that is constantly creating new levels on a quantum computer. So here's a few examples. This is using level 1, 2 from Super Mario Brothers, which we use because it has a few features which are quite hard for our system to do. So it allows us to analyze properly how good it can do. One thing that we keep an eye on is pipes, because pipes are 2 columns wide in the way that we break things down into columns. And so the system has to be clever enough to be able to produce one side of a pipe and then produce the other side of the pipe. So in the original level, of course, you always get complete pipes. We have a parameter called the temperature, which we can tune to different values. If we have it very low, we get levels that are very boring, very sparse, but always know to put a pipe together. If we have the temperature at a higher level, it's essentially random and doesn't care about pipes, for example. But if we have it somewhere in the middle, it produces perfect little riffs on the original level. It's really nice. So that's if we do simulations, we get examples like that. But what if we run on real quantum hardware? Well, we find that if you throw every type of error mitigation you can at it, you get essentially perfect results. So it runs very well with error mitigation as well. So here in the middle, we see a level that was created on real quantum hardware. This actually didn't use any error mitigation. This was run on IBM's Garnet device and was run in a way that doesn't use error mitigation, because in principle you don't need to with quantum reservoir computing, but it still produces a pretty good level. If you don't use error mitigation though, sometimes there can be problems if you have a mismatch between the, the, the system you're using to train the data and the system you're using to actually generate the data. Often this can be that you're getting stuck in certain features. So for example, in the original level, we have these little platforms that only last a little, only last a few columns. But if we look at the level that was generated here on a real piece of quantum hardware, for some reason it's getting stuck on those platforms. So these are some of the issues that you have to look into when using real quantum hardware. And of course, that's the fun of using real quantum hardware. But we can get very good results too, either using error mitigation or other tricks. Of course, it's great when you're writing a paper, as we are writing, on how to use quantum reservoir computing for computer games, to use the classic computer game Super Mario Brothers, where if we actually want to make a game that people can play, then we have to make our own game. So that's what we're doing. We're making an obby on the platform Roblox, which is going to be constantly generated via real quantum hardware. So if you want to know more about that, check out the demo. We are also working on projects in the visual arts. However, it should be emphasized that unlike Quantum Blur, which is great but runs on a simulator, we will be doing things that run on real quantum hardware. This is very important to us going forward. We are a quantum computing company. We want to use real quantum computers and to show how you can build products based upon them. Which brings me to the outlook. We are a company that wants to build products even now, consumer-facing products based on quantum computers. This is not something that's very easy for other companies that really need to wait for a quantum advantage, especially since we might have to wait until fault tolerance before a quantum advantage comes. But the beauty of the creative space is that usefulness means something a little bit different. Of course, there are complex computational tasks in the creative space that need a quantum advantage and therefore probably fault-tolerant quantum computers, but there's also plenty we can be getting on with before we get there. So we are going to be learning the lessons that need to be learned to build consumer-facing products based on quantum computing that bring people something new and interesting and do so using the wonderful world of real quantum hardware. If you would like to join us on that journey, let us know. And we would love to collaborate because not only do we want to build products, we want to build products that are useful to people, which means talking to the people that they should be useful to. So, thank you for listening and enjoy the rest of this event.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.